Hi and welcome back to the next video in our series. This video is selected problems in Ohm's law. Let's get started. Before we do any problems, let's just remind ourselves of the three basic triangles. The current flow triangle. Current is the flow rate of charge per time, so it's Q divided by T. Potential difference is V, volts, is the work per unit charge. That's the push on each charge to get it through the circuit. And of course, Ohm's law is the push to flow ratio. That's current equals V divided by R, but also R is V divided by I, as well as V equals I times R. Let's take a look at problem number 1. The graph represents the relationship between the voltage across a metal conductor and the current through the conductor at a constant temperature. What is the resistance of the conductor? So when we look at this graph, we see on the y-axis, it's the potential difference V, and on the x-axis, it's the current in amps, which is really the symbol I. If we remember from our Ohm's law triangle, I is V divided by R. So that means V divided by I is resistance. So therefore, the slope of this line is the resistance. V divided by I is resistance. And of course, that gives us 10 ohms. So you could pick any place you want here, especially when the slope crosses the intersection of two lines. So you see 2 divided by 0.2, 4 divided by 0.4, etc. That's a slope of 10 ohms. Okay, let's take a look at the next one. Here's number 2, which is a quick fact. Conductivity in metal solids is due to the presence of free electrons. So it's the flow of electrons that causes conduction of electrical current through a piece of metal. Okay, here we have question number 4. A metallic conductor obeys Ohm's law. Which graph best represents the relationship between the voltage V across the conductor and the resulting current through the conductor? So this is back to the triangle. V equals I times R. So we have V on the y-axis, I is on the x-axis, and so the slope of that line is the resistance R, just like in problem number 1. And if we harken back to the Ohm's law triangle, we can see here I is V over R, R is V over I. The slope of V to I is R resistance. Okay, let's take a look at another one. Here we have in problem 7, what is the voltage across a 2 ohm resistor that draws 2 coulombs of charge per second? So when I see a 2 ohm resistor, I know that I'm dealing with the letter R for resistance. But when I see 2 coulombs of charge per second, I'm thinking of the flow rate of charge in the current flow triangle, Q divided by T. So that's a current value. I equals Q divided by T. So you have 2 coulombs of charge in so much time, and it turns out to be 2 coulombs of charge per second. That's 2 amps. So we just use the voltage triangle, and we get V equals I times R. We get 2 amps times 2 ohms, which is 4 volts. Let's take a look at another one. Okay, here's problem number 8, which is very similar to problem number 7. When a lamp is lit, it draws a current of 0.5 amps. The amount of charge passing through the lamp in 10 seconds is, and of course, we know that the relationship between Q and I and T, according to the power triangle, I is Q over T, Q equals IT, I times T. So the amount of charge is the current flow for so many seconds. So in this problem, Q equals I delta T. So you have 0.5 coulombs per second, which is what an amp is. That's the trick. An amp is a coulomb per second times 10 seconds. Cancel out your seconds, and you get 5 coulombs of charge. All right, let's take a look at another one. Here in problem 10, the graph shows the relationship between current and voltage for 4 resistors, A, B, C, and D. Which resistor has the greatest resistance? So when I take a look at these 4 values, A, B, C, and D, we see that the slope of A is higher than the slope of B, and B is higher than C, and C is higher than D. Then we look at voltage on the y-axis and current on the x-axis, and we remember the Ohm's law triangle. Here it is, which is also, of course, on the reference table. R is V divided by I, and we see the delta Y over delta X, so the highest slope should give us the highest resistance. choice A. Let's take a look at another one. Here in problem 17, moving 4 coulombs of charge through a circuit requires 48 joules of electric energy. What is the potential difference across the circuit? So we recall that the potential difference is defined as the work done pushing each charge through a circuit. So the work is energy, and 48 joules of energy is the work done pushing 4 coulombs of charge. So 48 divided by 4 is 12, and a joule per coulomb is a volt. Let's take a look at the potential difference triangle. V is W per Q. This is the work done per unit charge. So a joule per coulomb is a volt. The potential difference, or the voltage, is the work done per unit charge as the charge is moved through the circuit. The battery pushes the charge. It spends energy pushing those charges against the resistance in the circuit. Let's take a look at another one. Here in problem 21, which electrical unit is equivalent to 1 joule? So we know that a coulomb is an electrical unit equal to the transfer of 1 amp per second. So a volt is equal to 1 joule per coulomb. We can express 1 joule in terms of 1 volt and 1 coulomb. So we have a volt is 1 joule per coulomb. So a volt coulomb, or a coulomb volt, is a joule. And here you go. This is this kind of problem where electrical units get a little bit kooky because there's so many different ways of expressing different units, and the combinations of each are equivalent. So this is one of those. Joule equals volt coulomb. All right, let's take a look at another one. This is a problem from your Castle Learning. Question 4. A 330 ohm resistor is connected to a 5 volt battery. The current through the resistor is how many? Milliamps. See this little m here stands for milli. That's 10 to the negative 3. So this is an Ohm's law problem. R is V over I. 5 volts over 330 amps. And of course the answer turns out to be 0.0152 amps. But because we're dealing with milliamps, we take this number and we take the decimal and we move it over 3 decimal points, and you get 15.2 milliamps. And finally, we have these 3 problems, 6, 7, and 8 in the Castle Learning. This actually deals with something that does not obey Ohm's law. So light bulbs do not obey Ohm's law, and you can see that their graph is curved. While performing the experiment, the student noticed that the light bulb began to glow and became brighter as she increased the voltage, one of the factors affecting resistance. Which factor caused the greatest change in the resistance of the light bulb during her experiment? And the answer is 2. As the voltage increased, the temperature of the light bulb increased, which caused a higher resistance. So let's just take a look right here at the reason. Among the factors of a conductor that influences its resistance are the length, cross-sectional area, and temperature. Now we talked about resistivity, and we're going to do a lot more of that in the next video. The length and cross-sectional area of the light bulb material are constant. As the temperature of the light bulb increases, the resistance increases as well. This is a fact of non-ohmic materials. Now let's look at question 7. According to the graph, as the potential difference increased, the resistance of the light bulb also increased. So there's a temperature value, and now there's a potential difference relationship as well. The change in current is showing the effect of the changing resistance. The rate of change in the current is decreasing as the potential difference increases. As the current increases, this causes the light bulb to heat, which increases the resistance. This in turn affects the current. So you have more resistance, you have less current that gets through. And let's take a look at question number 8. It's the same light bulb, same graph, 3 times in a row, but they asked 3 different things. The student concluded that the resistance of the light bulb was not constant. What evidence from the graph supports this conclusion? Well, it's not a straight line graph. You don't have a constant slope when it's a curve. You have a changing slope. And since this slope down towards the bottom corner is steeper than it is in the middle and shallower as you get towards the top end over here, you see that your resistance slope is not constant. You have a changing slope. So the light bulb is worth talking about because it is non-ohmic. It does not obey Ohm's law, but has its own graph, which looks like this. The only questions you'll have to deal with about this on the regions are these three basic facts. Okay, thank you for watching. We'll see you in the next video.